Hello, and welcome back. Today we're talking about accumulation functions in applied contexts. We'll interpret the meaning of a definite integral in accumulation problems, and we'll determine the net change using definite integrals in applied contexts. Now, we've already looked at an accumulation function before, so let's just review that real quick. This says that the graph of the function g consists of a quarter circle and three line segments shown at the right. Let f be the function defined by the antiderivative from -1 to x of g of t dt. Okay, so what does that mean? That means that the derivative of f of x is g of x. And it's really important to write this down. Helps to organize your brain, but also you can now use that as a reference throughout the rest of the problem. So this definite integral means that we want the area under the curve from -1 to some particular x value. So we're going to take all these little shapes here and we'll put in some areas. We've got pi, 1, another 1, 2, and 1.5. And our particular problem is interested in going from -1 to somewhere else. So let's draw ourselves just a line here, knowing that that's kind of our baseline there at -1. Okay, so all we've done so far is read the problem and get our brain organized. So now let's start figuring out what we're doing here. Find f of -5. So this -5 we plug in for x. So we're looking for f of -5, which is the antiderivative from -1 to -5. But we have a problem with that because that's backwards. You can't go from -1 to -5. So we're going to have to flip those and put a negative in front. That's better. So now we've got negative, and now we're going from -5 to -1. So that's the area under the curve. So it looks like we've got pi from -5 to -3, and then a +1 and a -1, and those kind of cancel out. So we've got f of -5 equals -pi. Part B, find all the values of x on the open interval -5, 4, where f is decreasing. Well, we know that the derivative of f is g of x. So this whole graph here is the graph of the derivative. So f is going to be decreasing wherever the derivative graph is less than 0. F of x is decreasing on -2 to 1 because f prime of x is less than 0. Or you could say g of x is less than 0. Either way. Now let's write an equation for the tangent line to the graph at x equals -1. So in order to do that, we need a point and a slope. So if we go -1 to -1, we haven't gone anywhere. So we've gone 0. And then the slope, well, again, this is the derivative graph. This tells you the slope at any given point. So at -1, our slope is -2. So we have point, we have slope, we have the equation of a tangent line. Find the minimum value of f on the closed interval -5, 4, and of course justify. Well, minimums occur either at endpoints or where g of x changes from negative to positive. So we have to check both endpoints and this spot right here where g of x changes from negative to positive. Now actually, we already found f of -5, right? That was -pi. And then f of 1, that's going from -1 to 1, so that's -2. And then continuing on to 4, we would add this little 1.5 there. So f of 4 would be -0.5. So our minimum value is at x equals -5 and is negative pi. Okay, so now let's actually apply this. You receive a 10-week-old puppy. Yay! I love puppies. You receive a 10-week-old puppy for your birthday. He's growing at a rate of e to the 0.0125 t pounds per week. I'm not sure how you know that, but whatever. Where t is the puppy's age in weeks. At 10 weeks, the puppy weighs 14 pounds. That's important. What is the expected weight at the end of week 15? So we have this very slow growing function. And we know that at 10 weeks, the puppy is 14 pounds. And so what we need to do is find the area under the curve here, right, to know how much the puppy is going to weigh at the end of week 15. So we've got 14 plus the area under the curve of our function from 10 to 15. And you just pop that into your calculator, and the dear little fellow is going to weigh almost 20 pounds. Oh, now we're off to Disneyland. The Disneyland monorail is slowing down at a rate of 2t plus 25 feet per second, where t is the time in seconds. How many feet per second does the monorail slow down between t equals 1 and t equals 5 seconds? So what are we looking at? This is the graph of 2t plus 25, and it's labeled in feet per second. So that is an acceleration function. And what we want is feet per second. And we know that acceleration is the derivative of velocity. So we just need the area under the curve from 1 to 5 of acceleration. So we can take the antiderivative of that, which is t squared plus 25t, evaluated from 1 to 5, about 124 feet per second. Example 4, the number of liters of oil in a tank is changing at a rate of R of t equals 0.26 t liters per minute. So that's some sort of a velocity where t is the time in minutes. Initially, the tank contains 14 liters of oil. So that's going to be important. Find the amount of oil in the tank after 10 minutes. Okay, so we've got to start with 14 and then figure out the area under the curve from 0 to 10 minutes of that rate. So we'll take the antiderivative of 0.26t and evaluate that from 0 to 10. So there's about 27 liters of oil after 10 minutes. Now let's just take a moment to see if we can just interpret some expressions that we see. The function W of t gives the number of water bottles produced by a manufacturer by time t in hours on any given day. So what does that mean? Going from 4 to 8, the antiderivative of W prime of t dt, that would be the number of water bottles produced during the hours 4 to 8. What about this one? The amount of oil in your pickup truck is decreasing at a rate of R of t quarts per minute, where t is the time in minutes. So what does that mean? During the 4th minute, the amount of oil drained from the truck is 0.5 quarts. Part C, David got a gift of $500 from his grandparents for graduation. That was very nice of them. He deposited the gift into his savings account. David's savings grows each month at a rate of R of t hundreds of dollars each month, where t is the month of the year. Explain the following expression. Here's a 5 plus, so that's probably that 500. But then what does this mean? So by the end of the 12th month, David's account has a total of $2,400. Dang, I need to know where he is banking so I can get that account also. Tables and graphs. We have a school bus accelerating from 0 to 18 seconds. The data for the acceleration, A of t, okay, so this is all acceleration data, is recorded in the table below. If the velocity at time t equals 0 is 6 feet per second, so we've got some initial condition here, find the approximate velocity at t equals 18 using a trapezoidal sum. All right, back to Riemann sums. Well, just a reminder, the area of a trapezoid is 1/2 times the height times the two bases added together. Okay, so let's check the height of all of these. So 0 to 3, 3 to 6, 6 to 9, 9 to 12, 12 to 15, 15 to 18. So that's awesome. The height of each of our trapezoids is all the same. So 1/2 times the height, okay, that's 3. And then the trapezoidal sum, the quick way to do this is figure out how many times each base is used. So if we're going from 1 to 4, 1 is used once, 4 is used once, but then we go from 4 to 6, so 4 is used twice, 6 to 8, 6 is used twice, and keep going. So I'm running out of room. But only 1 and 10 are going to be used once. So by the end of our trapezoidal sum, let me clean this up and I'll show you what it looks like. We'll have 6, that's the initial condition, 1/2 times 3, that's 1/2 times the base, and then 1 is used once, 4 is used twice, 6 is used twice, 8 is used twice, 7 is used twice, 9 is used twice, and 10 only used once. So about 124.5 feet per second is that school bus velocity. All right, the graph below shows the rate in gallons per hour at which stormwater is being pumped from an overflowing canal. Find the approximate number of gallons pumped from the canal in a 24-hour period. Well, first, let's write this in calculus terms. Okay, so we're looking for the area under the curve from 0 to 24 hours. And since we don't have any kind of equation to just pop in for R of t, we have to approximate. And once again, let's go ahead and approximate using a trapezoidal sum. So we'll kind of figure out what our heights might be. We've got 0, 100, 4, 125, 8 is maybe around 135, 12 is about at 130. We've got at 16, it's at 110, maybe at 20, it's about 85. At 24, it's about 65. Okay, so good news is the base of each of those trapezoids is all the same. So again, we've got 1/2 times the height of each of them, that's 4, times, except for the first and last, each of these bases occurs twice. And you put all that into a fancy-dancy calculator, or if you want to do it by hand, go for it. So about 2,670 gallons we've pumped out. Cool. Okay, let's revisit marginal cost. That's the costs at the margins. Maybe the cost to purchase one more or to make one more little widget or something. Says find the cost to produce 50 widgets if the initial cost is 1,800 and c prime of x equals 155 minus 30x plus x squared. So starting with 50, we have an initial cost of 18, and then we just need the area under the curve of c prime of x, which would give us a cost of about $13,700. All right. So those are some applications of accumulation functions, and I will I'll see you next time, okay? Thanks for hanging in there with me.